Okay, let's get started. Welcome to lecture 6 of course Advanced Optimization and Game Theory for Energy Systems. Today we are going to talk about robust optimization, different variants of robust optimization, including adaptive robust. We will talk also about chance constraint programming and distributionally robust optimization. And still, we will consider market clearing problem as our fundamental problem that we will work on it, and we will implement different variants of robust optimization to this problem. But if you learn these techniques, you can implement to any convex problem. So before going in depth, and before that, first I have to say that this lecture was prepared, its first version, prepared by Dr. Christos Ordoidis, who was my former PhD student 3 or 4 years ago. Then I built on his slides, and now we have this slides. So I have to say thank you to Christos for building the first version of this specific lecture. So how many of you already knows about the robust optimization and you worked on a robust problem? You can just write yes in the chat box for me to get an idea how many of you knows. Okay, we are getting mostly no, but also there are a few yes. Good that, yeah. The answers no make me happy because you will have a chance to learn something new in this lecture. How many of you knows about chance constraint programming? Yes or no? There's one yes, but many no. Good. And what about the distributionally robust optimization? DRO. There is one yes, but many no. Good. So I'm happy because you will have a chance to learn something new. I have to say that this specific lecture is a bit more, I wouldn't say more intense than previous lectures, but there are a bit more materials in this lecture than others. So because of that, at some point, I will not go very deep in each technique, but the goal of this lecture is just to introduce each concept and to start initial point for you. And if you are interested, later you can go and read more about those techniques. So let's see. So specifically, the learning objectives of this lecture, specific lecture, is first is to define robust optimization problem. And then we will talk about the 3 different approaches to tackle and solve a robust optimization problem. And then later we will talk about chance constraint programming. We will talk how it is different compared to robust optimization and stochastic programming. And lastly, we will talk about DRO, distributionally robust optimization, which is kind of very advanced technique to model uncertainty. Recently, there were a great focus on DRO and its different variants. So it might be interesting for you to know why DRO is a very appealing technique nowadays. Good. So again, as our main references, I can suggest again these 2 books. But in case you would like to go deeper and learn more about the fundamentals of different uncertainty modeling techniques, these are the 2 very nice lecture notes. One both from Georgia Tech, one from Arkady Nemirovsky, the one above, and also the other one by Alex Shapiro, Darinka Dencheva, and Andrei Rosichinski. Both they are very amazing lecture notes, but not with the flavor of power and energy systems. But I'm pretty sure you can learn a lot by reading those materials. Good. So some recap from the previous lecture, because the same we will use the same example as the one in the previous lecture. So you realize that under stochastic market setup in the optimization form, we are seeking to minimize the total operational cost of the system in day ahead plus the total expected operational cost of the system in real time. Again, I'll use these two abbreviations a lot. DA stands for day ahead and RT stands for real time. And our problem is constrained by production limits, transmission network limits, load shedding limits, spillage limits, nodal power balance limits, all of them in day ahead and real time. So I will use the same case study, or not case study, let's say example as the one in the previous lecture. No network, 3 generators, G1 is fully inflexible, G2 is fully flexible. Then we have a wind power unit, and we have inelastic load to price. There's only one small slight difference today. Again, we have 4 scenarios with the same probabilities. We are going to start with scenarios. Later, we will get rid of scenarios, you will see. But to start again, I assume I consider 4 scenarios. But the only difference is that the last scenario, instead of 10 megawatt, based on the previous lecture, we assume that under the last scenario, the wind power production is 40. So the example is slightly different than the one in the previous lecture. So if we solve our case study example based on stochastic market clearing, stochastic programming, the results are a bit different than previous lecture because yeah, the scenarios are a bit different. But we will end up to this day ahead dispatch, 60 by cheap generator, 30 by expensive generator, 30 by wind. All demand, the demand is fully supplied, and the corresponding operational cost in the day at the stage is 1,200 because the production cost of G2 is $20 per megawatt hour. So it's 30 times 20, it's 600. Also, the marginal cost, the production cost of G1 is $10 per megawatt hour. So it's 60 times 10, it's 600. 600 plus 600 is 1,200. Then we see that, under real-time scenario 1, the wind production is 30, which is exactly the same as day ahead dispatch of wind. So it's unchanged. There is no wind deviation in real time. So then there is no change in the schedule of G1 and G2. While in scenarios 2, 3, and 4, always we have wind power excess. So in all of them, G2 as our flexible unit needs to provide down regulation, while G1 is unchanged because it's fully inflexible. The demand is not curtailed because load curtailment is a costly resource. And in one of the scenarios that we have the highest wind production, we have to have 10 megawatt spilled because we don't have a down regulation resource to absorb the additional wind power excess. And in other scenarios 2, 3, and 4, in all of them, we have the cost reduction in the real time because G2 doesn't need any more to produce. So this is our result. And our total expected operational cost here is 1,200, our day ahead cost, minus our expected real-time cost, all weighted equally. So it's 0, 600, 600, 200, all with minus sign. So at the end of the day, our total operational cost is 850. And please remember this number. But this is an expectation, right? If we go per each scenario, if scenario 1 realizes, our our system cost, our total operational cost will be 1,200 plus 0, so it will be just 1,200. If scenario 2 or 3 realizes, then our operational cost will be 1,200 minus 600, so it will be 600. And if the last scenario realizes, our system cost, our operational cost will be 1,000. So as you see, under different scenarios, we may end up in different operational costs for our system, but in expectation, it's 850. Clear? And as you see here, we have a very diverse, or how to say, broad range of cost over scenarios from 600 to 1,200, right? So the system cost, the operational cost in one scenario is twice than that in the other scenario. So we have a broad range of system cost over scenarios, right? Is it clear so far? Yes, very good. Now let's talk about robust, not stochastic market clearing, but still using scenarios. So still let's keep our scenarios. Again, let's assume that we have the same 4 scenarios. But in the robust optimization, we have a different objective function. We are trying to optimize our problem, not in expectation, but under the worst case scenario. In this case, that we have scenarios under the worst case scenarios, right? So here we have a bit more conservative attitude. We don't care about let's say the expected cost, we care about the worst cost that it may happen. And in our previous example, it was 1,200. That's the cost if scenario 1 realizes. Clear? So it's conceptually different than stochastic programming. We don't optimize in expectation, but we optimize under the worst case scenario, just to be conservative. So if using scenarios, we like to write robust optimization, it will look like this. I will explain it, but is there anyone, maybe you can check it out for a minute, and then let me know how we can interpret different constraints and objective function. Please check it for a minute, and one of you can unmute and explain. Anyone who is volunteer to explain what the formulation of this slide says? What is it about? Drake?
Sure. So the set of values that we're minimizing under remains pretty much the same.
Mm-hmm.
The difference being that the objective isn't to minimize the weighted average, it's to minimize the worst. And the way we do that is by changing the final 4 constraints rather than putting a scenario specific, well, in addition to the scenario specific balance, we also then put each one of the individual scenarios penalties or outcomes under the same joint limit. And so by minimizing a objective function that contains that joint limit, we will reduce it to the worst case loss.
Very good, very good. What is beta? Is it variable, Drake, or is it parameter?
It's a variable.
Yes, it's a variable. Exactly. It's an auxiliary variable, right? Okay. In the optimal point, what beta will show? If we solve the problem, the optimal value of beta, what does it show?
It shows the penalty of the worst scenario,
Instead
or
of
the real-time cost
penalty,
deviation of the
yes,
worst scenario.
yeah, I would say the operational cost of real time, the operational cost of the system in real time under worst scenario.
Okay.
You agree? Yes. Yes, yes. Is there anyone else that would like to add an explanation, or is there any extra, description? Any things to add? No, let me explain, Drake. You provided very good explanation. Thank you so much. So still we have our day ahead variables, the schedule of G1, G2, and wind power. Uh, Still here we have, yeah, again, the production adjustment of generator 2 as our only flexible conventional generator. We have our load shedding under 4 scenarios. We have wind split variable under 4 scenarios. I'll talk about beta later. The red box, again, is our total operational cost of the system in the day-ahead stage. Is the deterministic. And the blue box is our day-ahead constraint. We already saw it in the previous lecture. The red box here is our real-time constraints, here just for scenario 1, but we need to add similar constraints for scenarios 2 to 4. But what is different here than before is the new variable, auxiliary variable beta, and also the 4 last constraints. Note that, for example, this part is simply just our operational cost in real time under scenario 1. Our cost is the deviation, the production deviation of generator 2 and load shedding. So we have a similar cost for all 4 scenarios, and for all of them, the upper bound is beta. And remember, beta is a variable. So what it happens, since we are trying to minimize beta, so it means that here just we will pick the maximum beta that we achieved out of the 4 scenarios. And here it means that the beta, the optimal value of beta, will be systematically equal to our maximum production cost, not production cost, system cost, operational cost, over scenarios in the real time. Is it clear? This is the simplest way to solve a robust optimization, right? But with scenarios, using scenarios. But imagine we may have 1 million scenarios. So it means that we need to write this constraint 1 million times to achieve the optimal beta. There's Aquila say B is supremum. Which B? Achilles beta?
So you mentioned the beta, the parameter. So we're trying to minimize it, but it has let's say, an upper limit or a lower limit. Could you?
Beta is a variable. It's not a parameter.
Yeah, the variable. Yeah. So we're trying to minimize it because it's in the
Yes.
objective function, but
Yes.
it has an upper limit or a lower limit.
No, it's upper limit. It's upper limit. We are trying to achieve the minimum. You can check it out later. You will see systematically by this way you are getting the optimal beta, while beta is the worst cost. Right? Good. One asked if we have time intervals, how many betas we need? Still, we need 1, because there, if we have different time horizons, different time steps, again, we are looking for the worst real-time cost for all hours in the real-time stage. So again, we will need to have just 1 beta. Okay. If we solve this problem, we will get a slightly different day ahead and real-time dispatch. Giannis asked, is beta a free variable? Yes, it's a free variable. So we will get different solution, slightly different solution. The difference is that last time that the expected cost was 850, but here is 900. But last time the cost under each scenario, it was varying from 600 to 1,200. And 1,200 was the worst one. But here, for all scenarios, the total operational cost is identical and it's equal to 900. So in expectation, our cost is higher, but we don't have such a worst cost like 1,200. In all scenarios, the cost is the same, it's 900. Right? So it's kind of trade-off. Higher cost and expectation, but we don't have such a, costly scenario that ended up in $1,200 cost for the system. Clear? Any question? Hope it's clear. So what happened? So our only source of uncertainty in the previous example was wind power, whose production can be between 0 and 70. 70 is the installed capacity. So in the stochastic programming, what we learned yesterday in the previous lecture, when we're having a scenario, so we defined 4 scenarios, 30, 40, 60, and 70, with the same probabilities, specifically in that example, and then we minimize the total expected operational cost. But always we had a big, strong assumption that our 4 scenarios, they can adequately characterize the underlying set of the uncertainty. It means that the wind power uncertainty is characterized very well by 4 scenarios. This is the assumption that we had, but we don't know if that assumption is correct or not. Specifically here, most likely it's a very strong assumption, and it impacts the results. If instead of 4 we go to, I don't know, 10 scenario, most likely we will get a different solution. And the other technique, which is different conceptually and also from formulation perspective, is robust optimization. Here we don't care about cost and expectation, but we optimize our problem under the worst case scenario, right? And again, we assume that our 4 scenarios, they are good enough to represent the underlying uncertainty. So here we don't care about the old scenarios, just we care about the worst scenario. That's how robust optimization works. But there is a key point. We should not ignore the other scenarios while we are determining the optimal solution under the worst case scenario. Our solution should still be not optimal, but feasible for the remaining 3 scenarios. So we are not, let's say, excluding or ignoring the other 3 scenarios. Still, our solution should be feasible under those 3 scenarios. Clear? Any questions so far? John, John asks about computational burden. I'll talk about it later. You will see. Good. So, but in reality, I mean, we just how to say, by design we assumed 4 scenarios, but in reality, the worst scenario is not 30, right? The worst realization that may happen is simply 0. The worst outcome of the uncertainty, the worst realization of the uncertainty is wind equal to 0, right? But it wasn't one of our scenarios. So now we would like to get rid of scenarios and not to use scenarios anymore, right? And for that, in robust optimization, we need to define something called uncertainty set. Okay, so our input data in robust optimization is not scenarios, but it will be uncertainty set. And in our example, for our wind power producer, our uncertainty set is from 0 to 70. But if we assume we have 2 wind farms, but exactly identical wind farms, so wind farm 1 and wind farm 2, each of them, they can produce from 0 to 70, right? It means that now our uncertainty set is a box. We have a box uncertainty set. It means that any point within the uncertainty set, it could be a the true realization, the wind power realization of farms 1 and 2, right? And this is the simplest uncertainty set that you can think of. It's just a box with 4 vertices, right? With 4 vertices. That's the simplest uncertainty set that one can think of. Any questions so far? Clear? Good. But what is the worst case outcome in this? So John asked, do we need 2 wind farms? Yeah, I mean, for box uncertainty set, we need 2. Of course, if you have 3, then you will go for a cube and so on. Just as you see, by increasing the number of uncertain parameters, you also increase the dimension of your uncertainty set. Is it clear, John? Good. But here, assuming just 2 wind farms, which ends up to a box uncertainty set, where is the worst case outcome? It's 0, 0, as Neil said. Yes, exactly. This is the worst that may happen. Good. So just to remember, what is the objective of a robust problem? We are gonna determine our schedules under which we are going to get the optimal solution with respect to worst case. Here, trivially, we know that the worst case is 0, 0. But later you will see that the worst case point is not trivial. We need to endogenously achieve it. We can't easily say, oh, okay, this point is the worst one. But here in this example, it's trivial. So we are gonna find solution which is optimal for the worst case, but for any other point within the uncertainty set, our solution should provide a feasible solution. So optimal for worst case, feasible for any other point within the given uncertainty set. Remember, uncertainty set is given to our problem. Clear? Good. But uncertainty set in practice is way complicated to construct. It's more complicated than a simple box uncertainty. For example, here, that's a figure from the PhD thesis of my colleague, Stefanos Derikaraoğlu. Assuming that we have 2 wind farms, and assume that these green dots, they are historical data, and the 2 wind farms, they are correlated. It means that the worst, for example, for 2 wind farms, they will not happen at the same time, right? We can learn it from the historical data. And here, as you see, the uncertainty set, it ended up to a polyhedron, right? So how to derive uncertainty set, it's itself a big issue, right? So recently there are many papers talking about data-driven robust optimization. It means that how we can learn from our data, our empirical data, how to construct our uncertainty set. Hope it's clear. Now I would like to talk about the fun part of robust optimization. It's an interesting variant that we call it adaptive robust market clearing. How many of you knows about adaptive robust? Yeah, many know. Many know, which is good, Okay, nice. Again, we don't have any scenario-based approach. Forget about scenarios. We don't have scenarios anymore. What we need is uncertainty set. Okay. So the question is that we had this problem last time. I mean, 10 minutes ago, I talked about robust optimization in the market context. But there we had scenarios, and we could easily detect the worst scenario and optimize the problem against that. But now we don't have scenario anymore. We have uncertainty set. So the question is that how can we reformulate a robust optimization, for example, for our market clearing problem without having scenarios? And this is what we are gonna discuss in the next 10, 15 minutes. Clear? So let's get back to our original example, right? And if you remember, this is our real-time problem, just real-time problem. We are minimizing the cost in real time, which is consisting of the production of generator 2, the adjusted production of production 2, and the load shedding cost, and also all our real-time stage constraints. As you see, there's no scenario index there, right? So let's say for a single point, which point? What is omega here? Omega is our wind realization. So under wind realization, W, not omega, W, we are clearing the real-time market. And note that the all day ahead decisions, they are fixed. They are known in the real-time stage. Okay. So remember, in the robust optimization, we are trying to detect, yes, definitely. W is our wind production. So for given wind production W, here we are clearing the real-time market. So far, W is given, it's wind production, right? But the point is that in robust optimization, we would like to optimize the real-time problem under the worst case realization of W. And we don't know what the worst W is. Just we know that under the worst W, we will end up to a maximum real-time price. But how can we define the worst case W here without having any scenarios? Any idea? So I'm repeating, in the real-time problem, W is given, but we would like to find the worst case W and give it to the real-time problem. How to achieve it? Nico says at constraint W between 0 and 70. Okay, it means that W should be variable, but for real-time problem, W is given. It's not variable. In the real-time stage, we know what the realization is. So in the real-time stage, whatever we do, W should remain parameter, not variable. We have a lot of good correct answers here. So because of that, I go next slide. We need to go to two-stage problem, a max-min problem. So is there anyone who can explain what this max-min problem does? One of you can unmute. What does this problem? Sorry, what is this problem? No. I'm not saying what type of problem is it. What does this problem do? Nuran, maybe you can say a few words.
So it shows what would be the best action under a worst case scenario.
So what does the outer, I call it outer optimization, and I call this the inner optimization, right? So what does the outer optimization do?
Maximizes the outcomes from the real-time problem, which is defined by the inner minimization problem.
Very good, very good. Exactly. So can we say that the inner problem, the objective function is to minimize real-time cost under given W, and the outer problem tries to find the worst case W under which our real-time cost is the maximum. So this is why we are maximized here to get the worst case realization, while in the inner problem, for the worst case realization, for the worst W, we are minimizing the real-time cost. Is that correct?
Yes, that's also my interpretation.
Yes, I think also it's correct. And what is the constraint of the outer problem? It's this, right?
So it's only, yes, it's only the constraint with regard to W.
It's our uncertainty set.
Yes.
Our uncertainty set says that W is lying between 0 and 70. Thank you so much, Nuran. It was very good.
You're welcome.
Nima said, is this approach for when you mentioned that the worst case is not trivial? Exactly. Nima, if the worst case is trivial, it's trivial. We know what worst W is, so W is parameter. It's, for example, it's 0. We know it. But exactly, many times we will see it's not trivial what the worst case is. Then we need to add this maximization. Akila said, so finding the maximum among the minimum of the inner problem. Exactly true. Yes, it's fully correct. Finding the maximum among the minimums of inner problem with respect to W. Very good. So remember, W is a variable for the other maximization problem, but it's a parameter for the inner problem. Always for the real-time problem, the wind realization is given. Ingrid asked, explaining again the maximization of other problem. So the inner problem's objective function is this. We minimize the cost. The objective function of the other problem is this. So for the minimized cost for given W, we try to find the maximum cost. So we are saying that, okay, any W I give as the other problem, the real-time problem will try to minimize it. But what is the W that if I provide, the minimum real-time cost will be the highest? Is it clear? Nicholas said, how do we guarantee feasibility for all values between 0 and 70? That's a good question. So Nicholas says that, okay, let's say that its optimal solution is 0 or 70 or 50, which never happens. How to know that, okay, it's optimal for that point, but how to know that it's feasible for the rest of uncertainty set? Do you have any answer to Nicholas? It's a very good question. Is the question clear? Nikos, do you have any answer yourself? What type of problem the inner problem is? Is it convex or is it non-convex? It's a convex problem. We can check. You can check the value of objective function with respect to W, which is from 0 to 70, and you will see that it's always how to say increasing or decreasing. I can call it monotone. So because of the convexity of the inner problem, you can know that if your solution, if you find the worst case, also for the others, it's feasible. That's my interpretation. It comes from the convexity of the inner problem. My understanding is that if inner problem is not convex, we cannot ensure that our solution will be definitely feasible for the other points of the uncertainty set. Does it answer your question, Nikos? Very, very good. But it was a very good question. Thank you. So we talked about the objective function of the other problem, but does this structure seem familiar? Did we see it before? Exactly. Peter says, looks like the playbook for finding dual problem. Exactly. We already saw it. So Mahdi said, could the problem be max-max since we are looking for the worst case fin realization? If it's max-max, it means that for the worst case realization, you maximize the cost. Are we doing that? For the worst case, we are minimizing the cost. Very good. Nice. So we can say that this is the real-time problem. Who solves the middle problem? I will call it nature. Nature is against us, and here it reveals the worst case outcome. And now we have our day ahead market, right? So we have day ahead cost plus the worst case real-time cost. Is it clear? And as you see, there is no scenario. And here we are, for a given uncertainty set, we endogenously, within the problem, we find the worst realization within the uncertainty set. The uncertainty set itself is given. We endogenously find the worst case realization, and then we optimize the problem under the worst case realization. Any questions so far? It seems that it's clear to everyone. Yes, Jemima says, could you please go over how nature reveals the worst outcome? As I said, the nature, we assume that nature optimizes a problem. So the nature is the one who solves the maximization problem. So nature sees that, oh, for any W, we are minimizing cost. So nature thinks, okay, what is the worst W for us? So there, the nature maximize the real-time cost to find W, and then us in the real-time market for the worst W, we minimize the cost. John asked how to solve it. I have the same question, John. Good. Let me continue. This is a min-max problem, min-max, mean problem. And it looks quite complex to solve, right? And I think John agrees. So any idea how to solve it? John, do you have any idea how to solve this? Any clue? Yes, Nuran, or no, let me see. So John says the dual could be simplified as we did before. Farzad says KKT of the inner problem. Peter says dual. I don't know how to get there though. Husna says minimize the dual. Okay, Farzad, could you please unmute and explain what you mean? Let's go for KKTs. That's one of the alternatives. I totally agree.
Hello, everyone.
Hello.
The second stage is a bi-level optimization problem. We can derive the KKTs of the inner problem.
So the KKT of this problem?
Yes.
Okay.
It's going to be, I mean, they're going to be complementary slackness, but I'm not quite sure how to.
So KKTs will be added here. So
yes.
we have mean max problem, and the max problem has complementarity conditions.
Yes, we may be able to relax it or using BCAM.
Yes. Yeah, that's one of the techniques. I'll not go in depth, but then this mean max problem can be solved iteratively. I'll provide some references for that, but it's one of the techniques indeed. Very good. Then, John, you said duality. What is your suggestion? Would you like to unmute? Or maybe Peter? How can we solve it by dual? Why we are interested to derive dual? No clue? So Nuran says duality and then combine the two inner problems into one. Very, very good answer. Exactly, Nuran. As you see, this is max, this is mean, or the same objective function. If we make it max, right, then we can combine two max to end up to, so we can merge them to end up to a same max. How can we make mean, how can we change it to a max? We can derive duality. It's correct. But I have a stupid question. If you're trying to make it max, why not just not put a minus here for the whole objective function and then to make it max? Then it will be max max. Why we need to derive duality? Why not just to put, so as we know, the minimize f of x is equal to max minus f of x. So why not just we simply put a minus and then it will be a max? Very good, Jemima. Exactly. That trick will not work. If we put a minus here, this will be max, but now this will be min. So it will be min max. We didn't solve the problem. Very good. So one solution is that we replace the min problem with its duality. It will be max. Then we will have max max problem, and we can combine them. Is it clear? Yes. So back to lecture 1, duality. Raja says, just to be clear, here we should get w equal to 0, right? As that is worst case. Yes, intuitively w equal to 0 is our worst case, but it's not necessarily always intuitive, especially for complicated uncertainty sets with many vertices, with many wind farms, that we have a lot of vertices with correlations that 0, 0, 0, 0 never happens. Or in ellipsoid uncertainty sets, it's not easy to know where the worst case is. So here intuitively, yes. Adam said, so it's a rule that you can merge problems like that when they are both, yes. If you have a min-max or max-min problem, just take the duality of the inner problem, then you can merge them. Yes, always you can do that. Good, back to lecture 1. Why do you need to learn duality? Because everywhere we need duality, right? So we need to take the dual of this. So this is our inner problem. And I already remember W and they, not here, the day had dispatch, they are all parameters for the real time. So we have to treat them as parameters. So if you drive the dual of the inner problem, I worked on it yesterday. So I drive this. So as you see in the objective function, we have W, we have day ahead dispatch because they are parameters in the real-time problem. And this is our dual problem, which objective function is maximization problem. So what can we do? Let's get back to our min-max problem. So it was our primal problem. Now we have the dual problem. So the red box is our original inner problem, and the blue one is its dual counterpart, right? And they are equivalent if Slater conditions hold. And then, I mean, this is all the explanations. I said, now we can get rid of this. We can use this. It's max, max, so we can merge them. So we merge these two. And now we ended up to this problem. Now we have a mean max problem. Clear? I'll finish in 5 minutes, then we will have a break. Just I like to make sure that the robust part is finished. Any questions so far? And now, as you see, in the merge problem, W is a variable. It's a merge nature plus real-time problem. Is it clear? If you say clear, I'll be very happy. How do we merge the max problems? Yeah, just sum up the objective functions. Here we don't, yeah, we have just one object. Yeah. Let's get back to show here. Yes, it means that you get rid of this, you bring it here. So you have max over omega, max over all dual variables and something. So you can merge these two. So it will be one max and the variables are omega and all the duals. Yep, hope it's clear. Now we have a min max problem. Happier? But is there any issue here? Do we have any issue? Check the objective function. Do we have any problem? Remember, now W is a variable in the green box. Do you see any problem? Yes. We have the product of variables. Sorry, not there. Sorry, not this one. We have the product of variables here. W is a variable, lambda and mu6, they are variables. So we have bilinear terms. Now our maximization problem is not LP, it's a bilinear term. Exactly, so we have a nonlinear problem, but if we can solve the problem iteratively, assuming that W is given, then it will be LP. Remember, when we have, since our problem is convex, whenever we have box uncertainty or polyhedron uncertainty set, always the worst W is one of the vertices, either here or one of the vertices, right? So when we can do some iterative job and find the worst W. So I'm not gonna explain how to solve it more than that, because yeah, then we have to just talk one day about adaptive robust. But yeah, I'll provide some references how you can do that. But also, as I said, always we know that our worst case realization is one of the vertices. So also you can simply do that. Here we have two vertices, either 0 or 70, right? It's not even an answer, a box. It's just a range from 0 to 70. So worst case is either 0 or 70. So we can write an optimization problem like this instead of max min problem. But here the problem is that for each vertex, you need to add one constraint. If you have 1 million vertex, it means that you need 1 million constraints in this problem, right? It's not also very computationally appealing. So if you like to read more, you can read this book, the corresponding book chapter. Yes, if you solve the problem, you will see that yes, the wind dispatch under the adaptive robust is 20 in the day head dispatch, right? So yes, so far, is there any question? Yeah, Nuran also talked about yeah, 0 or 70 as the wind realization. 20 is the wind dispatch in day ahead. So the worst realization is either 0 or 70. 20 is not the realization. 20 is simply our dispatch in day ahead. Good. So let me, yeah, I think it's good to have a break of 10 minutes. So at 5:15 Denmark time, we will continue. See you in 10 minutes. Okay, let's start again. Do you have any questions so far? Is everything clear? If you're right, if you clear and yes, I'll be, yeah. So sunset it's clear for everyone. So let me conclude the robust part of the lecture. So we talked about uncertainty set as the main input data we need to give it to robust optimization. And if we think wind power as our forecast in the day ahead and the deviation or forecast error, if we have, for example, 2 wind farms with this range of forecast error for the 2 wind farms, we can end up to a box uncertainty set, something like this. And as I said, we will call it box uncertainty set. And our worst case realization always happens in vertices. So here we have, in the simple example, we have 4 vertices that we have to check which one is the worst case realization. So in general, the number of vertices in a box uncertainty as a function of wind farms. Do you have any idea how much how much is the number of vertices as a function of wind farms n? Any clue? Yes, Drake, exactly. It's 2 to the power of n. So if we have the 2 wind farms, then we have just 4 vertices. But if we have hundreds of wind farms, then we have a huge number of vertices. Then it's not very trivial to find which vertex will give us the worst case realization. So this is really why we need to endogenously achieve the worst case realization, right? Even in a box uncertainty set. But now we, based on our historical data and the correlation of our 2 wind farms, we can define this type of constraint that we can call it budget. So we can define budget type uncertainty set. And then here, our uncertainty set is not just a box, but it's a polyhedron, right? And the figures from the book. Do we have any idea here with budget type uncertainty set, how many vertices will we have as a function of n, number of wind farms? So here we have, for 2 wind farms, we have 8 vertices. So if you check it out, it's 2 to the power of n times n, right? Again, if we increase the number of wind farms by hundreds, it's not easy to check each vertex one by one and then to see which one will end up to the worst case realization. So this is why we really need adaptive robust optimization with a format of min max mean, and max finds the worst case realization for the given uncertainty set. And here in this lecture only I talked about polyhedron type uncertainty set. You can also think of ellipsoid type uncertainty set that we don't have vertex. Then we will have a totally different story there, right? If, for example, our uncertainty set is something like this as an ellipsoid, then we will have a different story. Cool. Good. I would like to just to conclude this part. Though I know I open a lot of questions in your mind, but I hope it's enough for you, as an initial lecture, just to learn the basics of robust optimization, how to implement it to power systems, and then you can think more and you can check more references, how each technique specifically it works. So for our initial min-max problem, I would say there are 3 different techniques in the literature how to solve it. One is based on deriving KKTs of the inner problem and then to solve it in an iterative manner. So we will have min-max, but max has a complementarity conditions. Then we need to solve it iteratively. You can check this paper from Ijor. The other one is replacing the inner problem by its dual, but the problem is that we will have bilinear terms. Again, we may need iterative solutions. It seems that it's the most popular technique to solve adaptive robust optimization. You can check these 3 papers from Bretsimas et al., Gian et al., and Marcus Zuno et al. You can check these 3 papers that use that technique. Also, the simplest is that go and check vertices one by one. It will be LP. It's I mean, from LP wise, it's easy to solve, but maybe you need to check millions of vertices, which is really hard to do that in large problems. Okay. So as a recap, in robust optimization, under which outcome of uncertainty do we get the optimal solution? Every point in the uncertainty set? Under which point in the robust optimization we get the optimal solution? Yes, worst. So for the worst case, we optimize the problem, but the worst case is not given. We have to update it while we are solving the problem. So this is what I call it endogenous finding of the worst case problem point. So what about the other outcome, other points of the uncertainty set? Do we know something about those cases? Yes, we know that our solution is feasible to any point in the given uncertainty set. So we know that we are optimizing against the worst case. So our problem, our setup is rather conservative. How can we reduce or control the conservativeness? By which input data we can control the conservativeness? Yes, by well structuring the uncertainty set, we can control conservativeness. If we shrink, as much as we shrink the uncertainty set, our solution is less conservative. Good. So now I'm going to talk about chance constraint. So if you have any question about the robust optimization, maybe it's the right time to ask. No question? Okay. Nikos asked, if we know beforehand the worst case scenario, can we run a single scenario? Yes, as long as you know that for other scenarios, your problem will be feasible. If you know exactly where your worst case is, and you make sure that your problem is always feasible, then yes, please go that. But if you don't know the worst case, or if you don't know that if you optimize for worst case, your solution is feasible for other points, then no point, no other way to do. We need to solve robust optimization. Do we agree, Nikos? Hopefully you agree. Priyanka says, in this method, is this method used in real world? I'm not sure it's being used in electricity systems. I know that in New England market, they were thinking about clearing the market in robust way. It was Yuiji Litvinov who was thinking of that, but he unfortunately passed away a couple of months ago. Yeah, his group was thinking about clearing the market in a robust way, not maybe exactly in adaptive robust, but yeah, in a robust, more robust way. In other industry, rather than electricity, if adaptive robust being used, to be honest, I don't know. Maybe in other sectors, in transportation, in others, it's being used. I have no clue. But we also have one problem in robust way of clearing the market. In any way, in iterative solutions or whatever, we may derive binaries. If we have binaries, then we will not be able to derive price that easy. So also we have to think, how can we derive price under in a robust market clearing problem? Yes, Hosna said it would be good for capacity markets, maybe, but also for expansion problems, capacity expansion problems, robust optimization could be a very good tool, right? But now, hopefully, you have a good understanding, at least conceptually, what robust optimization does. So let me talk about chance constraint programming. I forgot how many of you said you already knew what chance constraint programming is. Could you please remind me? We can write yes or no. So we have, yeah, we have some no, some a few. Okay, let's talk about chance constraint. It's somehow connected to robust optimization. So in chance constraint programming, the optimization problem, again, we don't have scenarios, right? So the optimization problem is formulated in such a way that the probability of meeting each certain constraint is above a certain predefined level, let's say epsilon. So here, compared to robust optimization, we allow each constraint to be violated to some extent. And by that, we are extending the feasible region, or you can say we are shrinking the uncertainty set, and this way we are controlling the conservativeness. Again, I'm repeating, we are allowing each probabilistic constraint, each constraint that depends on uncertain variable and parameter, we allow each constraint to be violated to some extent. Let me provide an example. For example, this is the deviation of generator G2 in the real time, and it should be lower than 30. And note that since we don't have a scenario, delta omega is our source of uncertainty. It's our forecast error or mean deviation in the real time. And all our variables, including the deviation, sorry, the adjustment of G2, it's a function of our forecast error or mean deviation. So delta omega is the source of uncertainty, and this is a variable, right? It's a variable. But delta omega now is a continuous probability function, probability distribution. It's not sampled by a set of scenarios anymore. So now we have this operational constraint for G2. And now we would like to know that the probability of this constraint hold over the whole point of the distribution, probability distribution, is greater than or equal to 1 minus epsilon. And epsilon is a value between 0 and 1. It's a given value. For example, if epsilon is 0.01, it means that in 99% of the time over the given probability distribution function, we like to make sure that this operational constraint will be held. But in 1% of the time over the given distribution, this constraint can be violated. So by disallowing to be violated, we reduce the level of conservativeness. So P is probability distribution of our underlying uncertainty. Here it's delta omega, which is the wind forecast error. And we assume that this probability distribution is given. I'll talk about this assumption later. This is our operational constraint. And epsilon, that you can call it risk parameter if you like, it's a given parameter, it's a given value, and its value is lying between 0 and 1. Right? So for example, if your probability distribution is something like this, whatever, so we like to make sure that if we sample our mean deviation over this probability distribution and plug into our constraint, in 99% of the time, that constraint is held. And in 1% of the samples achieved from our given probability distribution, the constraint can be violated. Is it clear? Very good. So remember, in chance constraint, we assume that we know, we have a perfect knowledge about the underlying probability distribution, the probability distribution of our answer. We assume that we know it perfectly. Later, we will relax it. Clear? Good. A specific case, if epsilon is equal to 0, it means that at any point of the probability distribution, we are enforcing the constraint. It means that the constraint, we can call it a robust constraint. We don't allow it to be violated. At any single point over probability distribution of delta omega, this constraint should be held. So this is a chance constraint programming for our famous example. It's the two generators, one wind farm, one load. So could you please check it out for a minute? And then one of you maybe can unmute and explain what this problem is. So Ianis, I will answer your question a bit later. Is there any volunteer who would like to explain what this optimization does? Anyone? Yes, Achilles?
Yes. So first we go to the objective function, and we see that we are minimizing over the expectation of the wind uncertainty. So it's similar, let's say, to the stochastic optimization approach, but instead of scenarios, here we have the expectation, which we can actually approximate with scenarios.
Mm-hmm.
And the first constraints are the same, and then we move all to the constraints that regard to the real-time, let's say, operation. And essentially, these are the same constraints as before, but we have imposed everywhere, let's say, a chance constraint. For example, let's say we want them to be satisfied 99% of the time.
Yes.
And
So,
we have, yeah.
So the probability of, for example, this constraint to be held with respect to given probability distribution should be low, sorry, should be greater than or equal to 1 minus epsilon. Epsilon is given.
Yes.
Very good, very good.
And essentially, we have removed all the scenarios, and we have the uncertainty in let's say distribution form here.
Very good, very good, very good, very good, very good, very good. Yes, exactly, Aklas, what you explained was very correct. Yes, exactly. Ianis asked, you said the probability is known as an empirical, or can we say that we define a set of scenarios or whatever? When I say the probability is given, it means that either we know exactly the type of distribution. For example, we know it's Gaussian or it's a beta distribution or whatever, or we have a huge data set, empirical data set with a lot of historical data. Again, if we assume that our data set, empirical data set, represents the the underlying probability distribution, then we can say it's known. But depending how we know it, is it we know the type, or we have a data set, the solution technique will be different. I will explain more soon about the solution technique. But thank you, Achilles. Again, we have day-ahead variables, and we have 3 real-time variables. As you see, we don't have scenarios anymore, but our variables, real-time variables, they dependent on our uncertainty. For example, our load shedding for load D is a function of delta omega. And remember, delta omega is our source of uncertainty. It's wind deviation in real time. So we have 3 variables in the real time like this: one for adjustment of generator G2, one for load shedding, one for wind spillage. So as you see, these variables, they appeared everywhere in the real-time constraints. Then we have, as before, the total operational cost in the day-ahead stage. It is a deterministic part. But now we have total expected operational cost of the system. This is the expected operator over, or with respect to, probability distribution P that we know it's given. For us, it's given for now, right? So just we got a probability distribution. So the question is that, well, we don't have scenarios. How can we get rid of this expectation operator? Remember, we don't have scenarios. And then again, we have day ahead and real-time constraints. And remember, all our inequalities, we have one chance constraint per constraint, or per operational constraint. We will call it individual chance constraint. You could also think of joint chance constraints. For example, if you have a probability of 2 constraints, h of x is lower than or equal to 0, and g of x is lower than or equal to 5, the probability of these 2 constraints together to be held should be greater than or equal to 1 minus epsilon. Then we call it joint chance constraint, right? But here we formulated it as individual chance constraint. Both of them, they are solvable, but the joint chance constraint is more challenging, right? But here in this course, I only focus on individual chance constraints. Here in joint chance constraint, you need to have only 1 epsilon, but here you need to have 1 epsilon for each constraint, and its values could be the same, could be different. We don't need necessarily to have the same epsilon for all constraints. But again, the question is that how can we get rid of chance constraint? How can we reformulate them to be able to solve the problem? At this form, the chance constraint programming is intractable. We cannot solve it. We need to reformulate the objective function, the expected term, and also the all chance constraints to be able to solve the problem. Is it clear so far? Any question? Is it clear? Can you confirm that everything is clear? Okay. But how can we solve chance constraint programming? We have in general 2 approaches, either analytical reformulation or sampling-based approach. So depending on our given probability distribution of the underlying uncertainty, if it has certain properties, I'm not going to list those properties, but for example, our distribution should be unimodal, and so on. Just check references 1 and 2, the paper of Nemirovsky and Shapiro. Also, you can check PhD thesis of Lena Holt from ETH. Now she's at the University of Wisconsin. She also applied chance constraint programming to power system problem. So if we have some certain properties in our underlying probability distribution, then we can exactly reformulate our chance constraint. We can reformulate in a way that we can solve it. For example, the Gaussian distribution. If our probability distribution follows a Gaussian distribution, then we can analytically reformulate our chance constraints. And if we do it, the resulting model, each individual chance constraint will be replaced by a second order constraint with quadratic terms. It's convex, but not linear. But under some extra assumptions, it will be reduced to a linear program. So again, you can check these two references. Also, there are many references, many papers in the last 2-3 years that implemented chance constraint programming with analytical reformulation, assuming that the underlying probability distribution has some certain properties. But if we don't know about the type of our distribution, we just have a huge empirical data set from historical data, and they do not necessarily follow a specific distribution, or we don't have the properties that explained in references 1 and 2, then analytical reformulation is not an option for us. The only way is to solve chance constraint programming using samples. So we need to provide a lot of samples over our given probability distribution and then solve our problem using like a scenario-based stochastic programming. But how many samples, how many scenarios do we need to make sure that our scenario-based stochastic program represents well a chance constraint? I'll talk about it in the next slide. But is there any questions so far? Is it clear? Are you following? I'm just getting yes from a few people. Good. So sounds that it's clear to everyone. So assume that we have, we have this chance constraint, and assume that we don't know the type or properties of our given probability distribution. It might just have a set of historical data. So what can we do? This is a very nice paper from Margelos et al. Kostas Margelos and his colleagues. This paper proves that to be able to represent exactly a chance constraint, we need n number of samples picked or generated from the given probability distribution. And this number should be this. And here epsilon is our risk parameter, E is Euler number, nx is number of decision variables, like day-ahead dispatch, real-time dispatch, whatever. And beta is the level of confidence it's given. And this operator picks the smallest integer higher than the argument. For example, if it's 1000.1, it means that it should be 1001. But to get an idea how many samples we need to be able to recast chance constraint as a scenario-based stochastic program, for example, for IEEE 24 node reliability test system, that some of you are currently using it as your test case with 6 wind farms. Let's say beta is 0.0001, epsilon is 5%, and for 25 time periods, if you plug it to this equation, you will see that we need almost 87,000 samples. Last lecture, we solved a scenario-based stochastic program with 4 scenarios. Here, to be able to represent our chance constraints with these numbers, we need 87,000 samples to be generated from the given probability distribution. It's a huge number. But if we do that, if we solve our problem using a scenario-based stochastic programming with 80,000 samples, we guarantee that our constraints, chance constraints, are satisfied not only in sample, but also in out of sample. It means that if you go beyond 87,000, if you derive 1 million samples and you check, still you will see that in 90% of the times your constraint is held. So you provide guarantee in out of sample. That's the beauty of chance constraint with respect to scenario-based stochastic programming. You provide guarantee for the satisfaction of your constraints in out of sample. Is it clear? Yes. Yes. You don't need to provide samples differently for each sample. You can check for different constraints. You can check the number of the samples, the number of the number of samples is the same, right? For all chance constraints. N of X is the same for the whole problem. Beta, okay, maybe epsilon is different for different constraints. You can check for which constraint you need the maximum N, and you can pick that maximum N. Right? And it's the same story for joint chance constraints. So it's computationally hard to solve, but later, not today, later in the course, we will talk about the composition techniques. Yes, yes, Yanis. Yes. So sampling approach for chance constraints. With this formula, we need to sample over the given probability distribution. And as the number of samples tends to infinity, it means that our samples can better approximate the underlying probability distribution. It's intuitive. Right? So that's one way to recast. So we learned two things so far. If our probability distribution has some good certain properties, we can reformulate chance constraint analytically, then it's easy. The life is very easy. We don't need to have any sampling. If we don't know what type of probability distribution we have, or if we know what it is, but it doesn't have those properties, then we need to sample. But we need a huge number of samples, right? And then we can solve chance constraint problem as a scenario-based stochastic program. So far, there are two techniques to solve chance constraint, right? Can we solve chance constraint not analytically, not using scenario-based stochastic programming, but using robust optimization? Any clue? And if you read the title of the paper, it says that on the road between robust optimization and scenario approach for chance constraint. So it seems that chance constraint can be recasted either as a stochastic program or robust. How can we recast chance constraint as a robust optimization? No, I'm not talking about distributionally robust. We have a given probability distribution. How can we recast it as a robust optimization, the chance constraint problem? It's not about distributionally robust. It's something else. Drake says, rather than selecting the worst, we can select the nth centile worst. Remember, for robust optimization, you need uncertainty set. How can we get uncertainty set out of our samples? Exactly. Adam said, build uncertainty set from samples. Thank you, Adam. You know how many samples you need to produce. Build it. Sorry, generate the samples, then fit uncertainty set around all the samples you got. Right? So based on n samples, you have these samples. You arbitrarily pick samples, but their numbers comes from this formula. Then you can fit a box uncertainty set, but it will be, as much as you have more complicated uncertainty set, you can provide a better fit to your samples. Or you can provide a polyhedron, a budget type uncertainty set, or you can provide ellipsoid uncertainty set. So just you need to fit all your samples within the uncertainty set. Then you have the uncertainty set. Then you can solve your problem as a robust optimization. Is it clear? Raja said, when we cast it as scenario-based stochastic program, we consider all samples having equal probability. Yes. Yes, it's sampling. Yes. Yes. So it's like sample average approximation. Yes. So you see chance constraint is a generalized model. You can either solve it analytically if it's possible, or you can recast it as either stochastic program or robust optimization. Adam said, do we need binaries to solve this problem with samples? Why binaries? If you're thinking about adaptive robust, maybe, but I don't see why we need a binary at the first place. Okay, so, but remember, I'm not saying that the solution of stochastic and robust will be the same. Usually, the robust optimization provides a more conservative solution for chance constraint. If you like to read more about chance constraint, I think it's very interesting technique. Do that. I found this paper very nice from Daniel Bienstock, Misha Chertkov, and Hernet. It's a really nice review paper. You can check it out. It's related to OPF problem, how to implement chance constraint to OPF problem, and use analytical reformulation. Then also this book by Bental et al. It's really good. Also, there are very nice presentations by Professor Shabir Ahmed, who also unfortunately passed away last year. This also presentation is very, very good. So recap, for a given uncertainty set in the robust problem, how can we reduce the conservative? We can use chance constraint, right? We allow some constraints to be violated to some extent. Is the assumption of having knowing the underlying probability distribution, is it a strong assumption? Yes, usually it is. We assume that we exactly know what the probability distribution of wind forecast is. In general, we don't know that much about it. So how to solve the problem while we are not confident about the underlying probability distribution? We can use the arrow. So I like that we go for, sorry, today is a bit long lecture. I suggest we go for a 10-minute break again. Then after break, I'll talk about DRO, but hopefully it will not be longer than 25 minutes. But before taking another break, is there any question? Kelly said, could you repeat, clarify, when we use robust approach for chance constraint, we do not guarantee feasibility as we did before, right? We guarantee feasibility for 90% of the times if epsilon is 5%. Yes. Good question, Kelly. Any question else about, did you like chance constraint? Is it something that excited you? Yes, Adam?
Hi, can you hear me?
Yes.
Yeah, thank you, Jalal. I'm still thinking about these binaries questions that I asked previously, because when you generate the samples, then you have to somehow count how many times you satisfy the constraint, right? Because you have a set, for example, in case of this IEEE 24 node.
No. When you use those number of samples, you don't need to count how many times it got satisfied. It will be satisfied. That's the magic, the beauty of that equation, formula to get how many n we need. You need to know how many samples you need, then solve your scenario-based stochastic program. Done. You can make sure that with out of sample, there's a guarantee that 90% of the time your constraint is hold. You can check it later, but it's not a part of the solution technique.
Okay, but then the probability distribution should also be constructed in a way that it will make feasible samples. So I mean, for example, for our problem, we won't have a situation that our probability solution, we have a sample that, for example, makes a solution infeasible. Can it happen, or am I?
Yeah. As I said, this is your underlying probability distribution. Based on the formula, you realize you need 100,000 samples. You take the samples, so now you have 100,000 samples, and now you solve your problem using scenario-based stochastic program, right? Done. Now, if you do expose the out-of-sample analysis, right? This time you can take 1 million scenarios instead of 100,000 and check it out. You will see that your problem will be infeasible in 5% of the times. That's what I'm saying.
Oh, okay, thank you.
Lars asked, were you saying that the chance constraint program with epsilon equal to 0 is not equal to the robust program? If so, can we elaborate why? No, I'm not saying that, Lars. If epsilon is equal to 0, then it means that our constraint should be always satisfied. So it's the same as robust optimization. So I didn't say what you wrote. Am I clear, Lars? Yeah, maybe I said something wrongly, but yeah, I corrected it. If epsilon is equal to 0, it's the same as robust optimization. It's always feasible for any point of the probability distribution. Good. It's 2 minutes to 6. Sorry that it goes beyond the time. So let's get back 6:10 p.m. It means that 12 minutes from now, I'll not take your time more than 20 minutes. I think DRO is a very interesting solution or method. I think you will like it. So maybe it's worth of waiting a bit more and hear about DRO. Yeah, so let's continue in 11 minutes. See you. Okay, I'm recording. Yeah, I forgot to record a few questions I just answered, but yeah, anyway, it happened. So now we are recording. So let's talk about DRO. How many of you knows what DRO is, or based on the explanations I had so far, you can guess what DRO will be? Distributionally robust. It means that it should be robust against distributions. Already I had assumption, or we had an assumption that in chance constraint programming, we exactly know the underlying distribution of the uncertainty. Any guess how DRO is gonna relax that assumption, or how DRO provides a generalization? Any clue? Any initial guess? Please feel free to say something, even if it's wrong. No worries. So Nuran said, if we don't know the distribution, then formulation which would be robust to assumption and distribution. Very good, Nuran. That's totally correct. Akila says, maybe we assume normal distribution, but mu has a standard error. No, we are not gonna assume any specific distribution. Rafa said we can relax the assumption that we know the probability distribution. Yes, definitely. But if we don't know the true probability distribution, then what to do? That's the question. Raja said, but in sampling-based method, we didn't assume the knowledge of distribution. Oh, we did, Raja. We did. We said that either we know the distribution or we have a data set from the historical data, and we assume that that historical data set represents the true distribution. But can you assure that the historical data really show the distribution, especially if the data set is not vast, if we have a limited empirical data? Now, even in the sampling-based method, we assume that we know the distribution. Okay, so let me, yeah, it was a good start for DRO. So let me continue. So here we relax the assumption. So here we assume that we don't necessarily know the probability distribution of our underlying uncertainty, right? We don't know what is the real, the true probability distribution of our uncertainty. And in general, it's true. We don't know the wind forecast error, what type of distribution, what is the true distribution for our wind forecast uncertainty. So still, we will use a chance constraint also to make sure that our probabilistic constraints, they are holding with a probability of equal to or higher than a certain level, 1 minus epsilon. But if I compare robust and distributionally robust, robust optimize under the worst case realization of a given uncertainty set. And we optimize the worst case cost, while in DRO, we find the worst case distribution, not worst case scenario or realization, worst case distribution in a given ambiguity set. So if we are finding the worst distribution, it means that we have a bunch of distributions that we call it ambiguity set. So we have an ambiguity set with a lot of distributions. Then we are trying to find the worst distribution. And then for the worst distribution, we optimize an expectation. Is it clear? Very good. So we are trying to be robust against distributions. But for the worst distribution, we optimize an expectation. Okay. So again, our typical problem. So here there are a few things that you have to be careful. One is calligraphic P, right? Our problem is mean max. So we are minimizing the total cost under the worst case. Yeah, we will talk about that. Before that, I need to define the calligraphic P. Calligraphic P is our ambiguity set. It's a set of distributions. How many distributions do we have in our ambiguity set? in general, you will see it's infinite number of distributions we have in our ambiguity set. So every distribution in the ambiguity set, it might represent our true probability distribution. We are not sure about true probability distribution, so we built an ambiguity set that includes either finite or infinite number of distributions. I'll talk how to build it later. And then so this is our ambiguity set. It's calligraphic P so far. So why do we consider a set of distributions instead of knowing a single one? The reason is that we don't know the true distribution. So instead of having a single distribution, we go for a set of distributions. This set might include infinite number of distributions. We will talk soon how to build such an ambiguity set. So far, assume that we have that ambiguity set. So now within the ambiguity set, we are trying to find the worst distribution, the distribution that ends up to the maximum cost. But we are selecting that distribution endogenously. It means that while we are solving the problem, we also find the worst distribution. But now we picked the worst distribution. Now we should do what? We have to solve again for the worst case realization of distribution? No, it becomes too conservative. For the worst distribution, now we optimize an expectation. So as you see, this P is the same as this P. So for the worst distribution, we optimize an expectation. Is it clear? Or it's complex? Priyanka, very good. I'll talk about that later. Priyanka said it looks like a combination of robust and stochastic program. Very, very good. I'll talk later why DRO is a generalization of a stochastic program and robust optimization. Priyanka, if you say how it's a generalization, I'll be very pleased. Can you guess from now why DRO is a generalization of stochastic program and robust optimization?
Well, based on what I've understood so far, looking at the expectation term, it gives me a feeling of the stochastic programming part that we were discussing yesterday, because there also we look at the scenarios and so on. Similarly, we are picking up one of the probability distribution here. So that is related to the scenarios, and then the robust because we are choosing the worst probability distribution.
Yes. Priyanka, can you say, what should I do with the ambiguity set? What should I do with that to recast DRO as either robust or stochastic program? Well, let me reword like this. This is my ambiguity set, this one. Okay. If I enlarge it, make it bigger and bigger to put more distributions there, am I going toward robust or I'm going toward stochastic program?
Yeah, maybe stochastic. It's no answers. It's like because you constrain more scenarios.
No, distributions. Our ambiguity.
Oh, okay, more distribution. Yes.
Before, as I said, it should be infinite. But let's say, yeah, just example. Already we had 100 distributions. Now by enlarging ambiguity set, instead of 100 distributions, we have 1,000. Are we becoming conservative or less conservative? We are becoming more conservative. We are going towards being solved like a robust optimization.
Robust optimization, yes.
But other way around, if we start shrinking the ambiguity set, already we had 100 distributions. Now we shrink it to only one. We pick one as a very specific case. It means that we exactly know what our distribution is. Then what happens?
We are least conservative. That means it's robust optimization, or
Yes, it's Sahan says chance constraint, but if you select between stochastic and robust, which one is it?
then it's stochastic. Or?
Yes. Then within your ambiguity set, you have only one distribution, so you will pick it, and for that you will optimize an expectation. It's a stochastic program.
Interesting.
Is it clear?
Yes.
Yeah. Exactly. As much as you shrink your sorry, by shrinking ambiguity set, it means that we know we have a better knowledge about the distribution, so we go towards a stochastic program. By enlarging the ambiguity set, it means that we are not sure about distributions. We put whatever distributions there, we are becoming more and more conservative, right? So ambiguity set is our, how to say, degree of freedom to control our conservativeness. In addition to epsilons, epsilon was 1 degree of freedom. Also, the size of ambiguity set is the 2nd degree of freedom to be less or more conservative, to switch between a stochastic program and robust optimization. Is it clear? Hopefully it is. So, oops. So what is this term? Which cost? I know it's operational cost in real time, but I'd like to tell me the exact name. Priyanka, real-time operational cost. Yes, but what? Expected, worst case. What? I mean, I like to hear the full name. Rafa, you said something? Worst distribution, but also we have expected operator there. Thank you, Kelly. Worst case expected cost. It's the expected cost for the worst case distribution. So I call it worst case expected operational cost of the system in real time. Expected for the worst distribution within the ambiguity set. Very good. So as I said, we determine the worst distribution within the ambiguity set, and then we optimize the problem in expectation with respect to such a worst distribution. Is it clear? If you write a few clear, I mean, a few of you, I'll be sure it's super clear to everyone. Very good. Are they chance constraints, or Milad said, it seems that we solved the problem for different stochastic scenarios. Am I right? No, not for scenario. Here we don't have scenarios. We, no, Milad. We don't have scenario at all. We get scenarios from distributions. Here we have more than one distribution. So I don't agree with your expression, to be honest. Let me continue. Are they chance constraints that we already see, or they are slightly different? Are there chance constraints, or they are different? Any clue? Do you call them chance constraints? Yes, Nico says we have mean. Already we didn't have mean. Now we have mean at the beginning of chance constraint. Exactly. Marin says chance constraint, but additional mean. What does it mean? What that additional mean means? Goran says they are worst case chance constraint. Very good. We will call it distributionally robust chance constraint or ambiguous chance constraint. Let's go for distribution robust chance constraint, DRCC. So Goran, since you answered, for example, the first one, what does it mean? What does it enforce?
we make sure that in the worst distribution that the constraint is satisfied with 1 minus epsilon times or percent times.
Exactly. So we don't know we don't have a unique, thank you, Goran, it's fully correct. We don't know the real, the true distribution. So again, within the ambiguity set, we pick the worst one. For the worst one, we ensure that our underlying constraint is hold with a probability of minimum 1 minus epsilon. So now we have chance constraint enforced for the worst distribution, not for any distribution. Before the break, we assumed that we knew the distribution. Here we don't know, so we picked the worst one. Why it's minimum? Why it's not maximum? Goran?
If you would max it, then you would find the best case, right?
Exactly.
And then you risk that you won't satisfy it in other cases.
Exactly. Let me ask another question, Goran, maybe again to you or anyone else. Our ambiguity set, let me change the color. Here and here, and in every single distributionally robust chance constraint, they are the same. It's okay, right? No problem. I mean, we assume the same ambiguity set everywhere. But what about this P? Do we have a unique P everywhere? Or you think that P for different DRCCs and for objective function, they might be different? Do we have a unique worst distribution everywhere? Or worst distribution for different chance constraints and for objective function might be different? Yes, they might be different. Exactly. So we can't say necessarily that we have a unique distribution which is worst everywhere in every single chance constraint and in the objective function. No, each item may have its own worst distribution. Is it clear? Personally, I really like DRO. I found it very elegant setup. I don't know if you feel the same or not. We already talked about this. By enlarging the ambiguity set, we go towards robust optimization, and by shrinking the ambiguity set, we go towards stochastic program. Already, we talked about that. So yes and yes. So DRO somehow provided a generalized model linking robust optimization and stochastic program. This is what exactly Priyanka said before. Okay. So you learned what DRO does. We have ambiguity set, we pick the worst one, and we optimize an expectation in the objective function. In the chance constraint, again, we pick the worst one, and for the worst one, we ensure that our underlying constraint is hold. I mean, the probability of the constraint being hold is minimum 1 minus epsilon. Good. That's the whole concept of DRO. Conceptually, it's beautiful. Ambiguity set. We would like to build ambiguity set and put either finite, but in general infinite number of distributions within our ambiguity set. How to build those ambiguity set? Any clue? Aquila says from available data. I agree. DRO is a data-driven technique because we build ambiguity set based on historical data. I agree. But how we are building it technically? Yeah, Amin knows, Amin said moment-based and distance-based. So Amin, would you like to unmute and say a few words? How we are building the ambiguity sets? we have historical data. Historical data. Thank you. Now we like to build ambiguity set. How to do that? It's fine. I mean, no worries. Remember, this is a distributions, full of distributions. They are just data. How we can build ambiguity set that includes certain type of distributions that represent our historical data. A Snell set moment or distance. I think a Snell set in Spanish, momento or distancia. Snell, maybe you can explain. Okay, let me go. Let me explain. So far, the two common approaches to build ambiguity sets, to the best of my knowledge, they are either metric-based ambiguity sets or moment-based ambiguity sets. I'll explain each of them separately. Nima said, can we use classification machine learning? Maybe, but let me explain here, then maybe you can have extra ideas that later you can think of and work on that. Let me think first, explain the metric-based ambiguity set, or some of you call distance-based. It's also correct, distance-based or metric-based ambiguity set. What does it mean? Say that this is our historical distribution from historical data, but we are not very confident that the red P really is our true distribution, especially if our historical data is limited. So we are interested to build a green distribution P, which is close enough to red P. I'm talking about closeness or similarity. There are, I don't know how much you know, but there are maybe different techniques measuring the distance of two distributions. So one of the most famous one is Wasserstein distance that measures the distance of the two distributions. And in general, the Wasserstein distance represents an optimal transport plan that minimizes the cost of moving the probability measure, minimizing the cost of moving from the probability measure green P to the red P. There's a very nice slide in presentations of Professor Daniel Kuhn. He shows what does it mean, how Wasserstein distance works. But anyway, Wasserstein distance is a measure, is a probabilistic measure, shows how two distributions like the red one and green one, how close or how far they are. So it ends up to a number like 0.1, 0.2. Okay. So this is our ambiguity set based on metric-based, based on Wasserstein measure. So the center is our empirical data, empirical distributions, which could be a set of points, a data set. Then using Wasserstein distance, we say also rho, that we call it radius, it's a given. So we say that any distribution whose distance to empirical distribution is lower than or equal to rho, it should be included in my ambiguity set. So rho is the maximum distance that a distribution within the ambiguity set can take from the empirical distribution. Is it clear? So we have a distance measure. So we have at the center our empirical distribution, and then we build ambiguity set whose distance is close enough to the empirical distribution. So then this bowl is our ambiguity set. So any point in the bowl represents a single distribution. Is it clear? Good. We call this metric-based ambiguity set. Wasserstein is just one way. There are also other techniques like phi divergence. I forgot the others. There are also the other stances that you can use, but Wasserstein has good properties. You can read I will show the references why Wasserstein is a better measure than others. Milad said, I wonder if, for example, we have Weibull distribution for one parameter, can we build ambiguity set by changing shape parameter? Milad, I'm not sure again what you mean. Which parameter? And maybe you can elaborate on your question.
Excuse me, Professor?
Yes, yes.
As far as I know, Weibull distribution have got two characteristics. One is, as you know, shape factor, and the other one scale factor.
Okay.
Let's consider we use, for example, normal distribution. Okay. And can we use ambiguity set by setting actually different variances for our distribution?
Not sure. Maybe we can talk about it offline, Milad. But again, your empirical distribution could be anything. Even it may have it may consist of some data set without any specific distribution. We are not taking any assumption on our empirical distribution. Then we don't care about the type of distribution. Any distribution, with or without a specific type of distribution, as far as this distance is close enough to the empirical distribution, it should be within our ambiguity set.
Yes, yes. Thank you very much.
Yes, Yannick, if you're talking about the center empirical distribution, yes, it's coming from historical data. This distribution doesn't need to have a specific type of distribution. In Wasserstein-based DRO, just we say that in our center, we have 1,000 points from historical data, wind as either 0 or 10 or 1,000 or whatever. So we put a set of historical data in the center, right? And then still we can build our ambiguity set. Yes, yes. So Yannick, we don't need to derive specific distribution out of our historical data. We can represent our historical data as they are, for example, with 1,000 single points. Amin said, how should we choose Wasserstein radius? It's like epsilon. How can we choose epsilon? Or an uncertainty set of robust. How can we choose uncertainty set? All it's about conservativeness. As far as rho is, by reducing rho, we are being less conservative. By increasing rho, we are being more conservative. How to choose it? It depends on our risk attitude. How much risk do we like to take? So there is no optimal value for rho. It comes from our own preferences. Is it clear? Is it clear? Yeah. Any other question? Good. So I will not explain you how to reformulate your problem to end up to a convex problem. Itself is a very long paper. I put it in the references, you will see. But the resulting model, that's the beauty. It looks a very complex model, but at the end of the day, under some specific cases, the problem is a linear program, which is very efficient to solve. Very efficient to solve. The other way that we can build ambiguity set is moment-based ambiguity set. So again, this is your historical data, right? It's just some samples, not samples, some historical data. You calculate the moments. The first order moment is mean. The second order moment is covariance. The third is, I don't know, skewness, whatever. But at least you can calculate the first two moments, mean and covariance, from the historical data. And then you can say that my ambiguity set includes all distributions that have the same mean and covariance. Right? It's moment-based ambiguity. It's the easiest one, less complicated than Wasserstein-based DRO, but maybe a bit less elegant. Right? So you say, for example, from here, the mean of my I don't know, empirical distribution is X, the it's a vector X, and our covariance is matrix, let's say zeta, or sigma, sorry, and then any type of distribution that satisfies mean X and covariance matrix sigma, they can be in my ambiguity set. Then we call it moment-based ambiguity set. It's again data derivative, right? But it's not based on the distance metric. Of course, you can think how to make your ambiguity set realistic. For example, by adding this third moment, or saying that, oh, also my distributions within the ambiguity set should be unimodal, always should have one mode, one pick. The distributions with the same mean and covariance, but with two picks, which are not unimodal, they should not be included in my ambiguity set. So always you can think how you can build your ambiguity set as far as later you can reformulate your problem and to write it in a tractable way. Hope it's clear. Yeah, that's the all things I'm going to talk about DRO, because yeah, it's like a course. If I talk about different types of DRO, how to reformulate, blah, blah. My intention was just for you to understand the concept of DRO. This is a very nice paper using moment-based DRO with chance constraints, with I guess individual chance constraints applied to OPF problem. This is one of the first papers about DRO, moment-based DRO, with, as you see, with the first and second order information. This is a very nice paper about metric-based, Wasserstein-based DRO that ended up in a tractable formulation for Wasserstein-based DRO. This is, again, very nice paper about moment-based DRO with inexact moments. Sometimes you say that, okay, my mean and covariance is this, but I'm not sure about that, so I allow my moments to be violated. Instead of saying my mean is 10 megawatt, you can say any distribution whose mean is from 9 to 11 could be in my ambiguity set. So it's a very nice paper with moment-based DRO with inexact moments. And also this is the links for video lectures of Professor Daniel Kuhn from EPFL. It's videos that when he presented his work at DTU about, yeah, he presented actually this paper, not this paper, sorry, the other paper, this paper about the metric-based DRO. So I hope this lecture excited you, and now you would like to learn more about DRO, different types of DRO, and implemented it. These 4 papers and these videos, they could be a good start point. But if you have any more, questions or whatever, you're always welcome to contact me, and I'll be happy to discuss with you. Yes, Sand, you're asking about step 2, so maybe we can talk about it later. Lars, you said about page 146. So which slide? Because I don't see the page number. Lars, is it here or?
I don't see slide numbers also, but it was quite a bit earlier actually on DRCCs.
Here. Yes.
Yeah, there, that slide, exactly.
So what is the question?
So those are kind of individual chance constraints for different distributions, right?
Yes.
Isn't that two? So that means that for one constraint, a distribution A might be the worst case. For another constraint, distribution B will be the worst case.
Yes.
But these distributions are for the same set of variables. So isn't that overly conservative? Because in reality, it will only be one distribution that realizes itself.
Yeah, that's a good question. Lars is asking, individual or joint chance constraint, which one is more conservative, right? So I think it's very case dependent. Also think of that. Here in individual chance constraint, you allow every single constraint to be violated to some extent, dependent on epsilon. So let's say every single constraint is allowed to be violated by 5%, right? So in total, if you check, the violation is more than 5% because each constraint itself can be violated 5%. So in general, if you check, you may see that in 50% of the times, at least one of the constraints is violated. But if you go for joint chance constraint, it's always 5%. So my interpretation is the other, is opposite. Individual chance constraint is less conservative than joint one. Do you agree?
That's right. Can I ask? Can I correct my question then? It's more about that we minimize in each constraint. We minimize for the set of distributions.
Yeah.
And then we take the worst case of all distributions, and in the first constraint, distribution A might be the worst one. In the second constraint, distribution B might be the worst one. But these two constraints share the same variable.
I agree. This is why I don't have a rigid answer to you. In the way you say yes, individual chance constraint might be more conservative, but also the way I'm explaining, I don't know if you you agree with me or not. With individual chance constraint, we allow every single constraint to violate, while in joint, all of them together, they have some limitation how much they can be violated altogether. So in that sense, individual is less conservative. So again, I'm saying it's case specific at the end, which one will be less or more conservative. But I'll be surprised if joint chance constraint is less conservative in general.
Yeah, I agree with you on that one. I just thought if there's a better way to still have individual chance constraints, but to select the one single distribution that would be the worst case for all of them, but with individual chance constraints.
I agree. Also, I mentioned in one of the questions, chance constraint is just one way. You can also think of CVAR constraints. There you can, control not only the frequency of the violation, but also the magnitude of the violation. So generally, CVAR constraints are more conservative than chance constraints. It's not something that I covered in this lecture. Sahan asked for step 2 of the course. Can we implement DRO? Yes, definitely. I'll be very happy if you implement DRO to your problem. Perhaps, but you need to read the papers to see how you can reformulate your problem from in a tractable way. Yeah, if you would like to go for DRO in step 2, let me know. I can provide you some more information how you can reformulate your problem. Just one last question that I can take. Any question else? Note that tomorrow there is no lecture. We have exercise and Q&A sessions. Then I can take all the questions that you may have. Good. So maybe we can conclude the session and see you tomorrow. Bye-bye. Thank you.